Welcome back. Problem 6-27. So statement is draw the shear and moment diagram for the beam. So you can see this is overhanging beam having a uniformly increasing load of magnitude W naught at this end. There is a roller support at point A while there is a pin support at point B. So we have to draw the shear force and bending moment diagram. So let's start with the solution. First step is that we will find if we remove this support at point A, so there will be a reaction force that is represented as RA. Similarly, if we remove this pin support at point B, so there will be a reaction force RB. So we will find this RA and RB. So how we will find? By using equilibrium condition, and first equilibrium condition is that sum of all movement about point B is equal to 0 and taking the counterclockwise movement as positive. So about point B, one movement that is produced by this force RA and perpendicular distance is this 2L by 3. The second movement that is produced due to this uniformly increasing load, so we will convert this uniformly increasing load into point load, and its magnitude will be 1 over 2 W naught into total length of the beam, which is L, and this will be acting at a distance of L by 3. This is the total length of the beam, which is L. Clear? Okay. So let's write that RA into perpendicular distance is 2L over 3, and it is producing clockwise rotation. So this will be negative. And what if we convert W naught, uniformly increasing load, into concentrated load? So this will be the load, and its magnitude will be 1 over 2 W naught into L. And that will be acting at a distance of L by 3, total length L by 3. Okay, and it is producing counterclockwise movement, so it will be positive. So plus 1 over 2 W naught into L, and perpendicular distance is L by 3. Their sum must be equal to 0. So it means that 2RA L over 3 is equal to W naught L square over 6. And from this we will get RA will be equal to W naught L over 4. So we have reaction force at point A is this one. Now we will find RB by using equations. The sum of all forces along y direction must be equal to 0, and taking the what force is positive. So one force is this one, the second one is this one, and third one is this one. Their sum must be equal to 0. So RA, which is W naught L over 4, plus RB, which we want to find, minus 1 over 2 W naught into L, is equal to 0. So from here you will get RB is equal to 1 over 2 W naught L minus W naught L over 4. So again, if you take the LCM, that will be 4. 4 divided by this 2 will be 2. So 2 into W naught L minus W naught into L. And then RB will be equal to W naught L over 4. So this is the reaction force at point B. Now what we will do, we have reaction force, so we will cut the beam for this section, and we will write the shear force equation. Let this distance is x. So what if I draw the shear free body diagram? So this is the beam where we have a uniformly increasing load. Now what will be the magnitude over here? So it will be, if this distance is x, so it will be Wx by L. The magnitude here, the magnitude is W naught. So when you cut the beam at a distance of x, so the magnitude will be W naught x over L. And when you cut the beam, there will be a shear force V, and there will be a moment M as well. So let this point is 1. So how we will find this equation of shear force? So by applying equation that sum of all forces along y direction must be equal to 0 and taking the upward force as positive. Now you can see that we have one force which is this one V and other one is this one. So what we, if we convert this force into a point load, so definitely this will be a point load and the magnitude will be equal to 1 over 2 W naught X over L into the perpendicular into this total length X. Their sum must be equal to 0. So I will write V minus V because V is downward. You can see over here. Okay. Minus this 1 over 2 into W naught X over L into X. And that will be equal to 0. Okay. So what we will get is V is equal to 1 over 2 W naught X square over L. And simply it will be equal to W naught minus W naught. V is equal to minus W naught X square over 2L. I will write it over here again so that V is equal to minus W naught X square over 2L. And let this is our equation number 1. And this is valid for X is greater than or equal to 0 and less or equal to L by 3. Now we'll write moment equation that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about this point 1, one moment is this external moment which is counterclockwise and it will be positive. The second moment will be due to this force into perpendicular distance is this which is X by 3 and load is this one. So their sum must be equal to 0. So M plus M is counterclockwise plus this will also this force will also produce counterclockwise rotation, so it will be also plus. So plus 1 over 2 into W naught X square over L into perpendicular distance is X by 3. Their sum must be equal to 0. So this total value is W naught X square over 2L which is mentioned over here, and this perpendicular distance is X by 3. So when you calculate it, you will get moment is equal to minus W naught X cube over 6L. And this is our equation number 2. So this equation number 2 is negative, so it means that our assumed direction of movement which is counterclockwise wrong, it should be in clockwise direction. So these two equation 1 and 2 are valid for X is greater or equal to 0 and less or equal to L by 3. Now what we will do is we will find the equation when we cut the beam over here. So this will be your total X. And here we have at a distance of L by 3 we have RA. So we will draw the free body diagram. So I will draw it. So again this is the beam. Clear? At this point we have RA and RA is W naught L by 4 and it is at a distance of L by 3. And let this total distance where you cut the beam is X. So there will be a shear force and there will be external moment as well. And we will have a uniformly increasing load. So again here what will be the magnitude? So it will be W naught into X over L. Clear? And what if we convert this uniformly increasing load into a point load? So Definitely I will draw it. So it will be this load, and this will be equal to 1 over 2 W naught X over L into perpendicular into total length of the beam, which is X. And again this will act, this distance will be equal to X minus L by 3, because this is total L, not X minus L by 3. It will be, sorry, X by 3. I will correct it, because this is X, so it will be X by 3. Okay, so what we will do is that we will, and this is for the region X is greater or equal to L by 3 and less or equal to L. So we will first find shear force by using this equation. So you can see here we have one shear force that is minus, the other one plus, vertical force is minus this, plus this W naught L over 4, their sum must be equal to 0. So I will write it minus V minus W naught X square over 2L plus W naught L over 4. Their sum must be equal to 0. So V is this one, this W naught X square over 2L is this one, while W naught L over 4 is this one. Their sum must be equal to 0. And from here you will get V is equal to W naught L over 4 minus W naught X square over 2L. So this is your equation number 3. What about moment? So we will apply sum of all moment. Let this point is point 2, about point 2 is equal to 0, and taking the counterclockwise moment as positive. So about point 2, one moment is due to this load, which is W naught L over 4, and perpendicular distance will be this one, which is X minus L by 3, because total is X, and when you subtract this portion, so X minus L over 3 will be this portion. Okay, and the second moment is due to this load, and perpendicular distance is X by 3, and third moment is this external moment, their sum must be equal to 0. So I will write it minus W naught into L over 4 into perpendicular distance X minus L by 3. Since it is producing clockwise movement, so it will be negative, plus 1 over 2 W naught X square over L into perpendicular distance is X by 3, and plus external movement, and their sum must be equal to 0. So from here you will get this movement will be equal to, after solving it, so let's solve that. This will be equal to W naught L over 4 into X minus L over 3 minus 1 over 6 W naught X cube over L. And this is the moment equation for region X is greater than L by 3 and less or equal to L. Let this is your equation number 4. Now we have all these equations. So what we will do is that we will draw the shear force and bending moment diagram. So for that I will, what I have to do is that if I rewrite this equation over here in order to draw the shear force and bending moment diagram. So V is equal to, first equation is V is equal to minus W naught X square over 2L. This was your equation number 1. Equation 2 was moment is equal to minus W naught X cube over 6L. This was your equation number 2, and they are valid for X is greater or equal to 0 and less or equal to L by 3. Similarly, for X is greater or equal to L by 3 and less or equal to L, we have the shear force equation, which was W naught L over 4 minus W naught x square over 2L. So this is equation number 3, and moment is W naught L over 4 into x minus L over 3 minus 1 over 6 W naught x cube over L, and this was your equation number 4. Okay, so we will draw the shear force and bending moment diagram. So let's start with that. For that I have to draw vertical lines from the end as well as from this edge. Okay, so this will be along the length, x will be in long and length, and here we will draw the shear force. At this point shear force will be 0. Now you can see at this end there is no shear force, so this will be 0 at a distance of L by 3. So we have this equation number 1. So at x is equal to L over 3, put in it in equation number 1. So when you put it in equation, V is equal to minus W naught into x square will be L square over 2 is 4. So 4 into 2 into L. So it will be equal to minus W naught L square over 8L. And it will be, if you further simplify, it will be W naught L over 8. So at x is equal to, this is your L by 3. This distance will be L by 3. Okay. So this will be L by 3. Okay. So we have W naught. Let W naught is this distance. Let this is minus value W naught L over 8. So you will get this point. Now you can see that shear force, the load is the first degree load, a straight line. So shear force will be a second degree line since the load is negative. So the shear force will be a second degree curve. So we will join them by using curve in clockwise direction. So it will be like that. Okay. Now at point A you have a load of RA which is equal to W naught L over 4. So W naught L over 4. So minus W naught L over 8 plus W naught L over 4 will give you, this is not 8, I think this is, let me check, this is 18, not 8. So this is not L by 2 here, this is L by 3. So this will be 9. So it will be 18. 18. So correct it, it will be 18. So there's this W naught L over 18 plus this load will bring the shear force to 7 W naught L over 36. So let 7 naught L over 36 is this point. This is 7 W naught L over 36. Clear? So shear force will suddenly change from this to this vertical line. Now what about the shear force for this? So for that we will use this condition for the shear force. So again you can see that this load is now decreasing, so shear force will be somewhere 0. So how we will find that location of x? So for shear force V is equal to 0. So put it in equation 3. So when you put it in equation number 3, so what we will get is that you will get shear force is equal to 0. So when you put it in equation number 3, so 0 is equal to W naught L over 4 minus W naught x square over 2L. So from here you will get x is equal to x square is equal to L square over 2, and upon further simplification it will be equal to L over under root 2, and that will give you 0.707 L. So it means at a distance of L is equal to x is equal to 0.70 L. So let assume that this is your half, this point is your 707 L. Let's assume this point is your 0.707 L. So your shear force will be 0 over here. And at x is equal to L, put in equation number 3. So when you put it in equation number 3, so you will get V is equal to, you can put it in this equation, x is equal to L. So you will get V is equal to minus W naught L over 4. So at this end, this shear force, let this is minus W naught L over 4. So your shear force will be like this one. It will be a curve type. This point must pass. Let me correct it. So it will be like that. So this is your shear force diagram. Now we will draw the bending moment diagram. So again, for bending moment you have to draw a horizontal line. Let this is your horizontal line, this is along the length of beam, and there will be a moment. So at x is equal to 0, if you put x is equal to 0 in equation number 2, you will get moment will be equal to 0 at this point. Okay, now at x is equal to L by 3. So when you put x is put in equation number 2. So when you put x is equal to L by 2 in L by 3 in equation number 2, so you will get moment is equal to L by 3, sorry. So you will get moment is equal to minus W naught, the equation 2 is this one. So we will put minus W naught L cube over 3 is 27 into 6 multiplied by L. And if you further simplify at the end, you will get 0.006178 W naught L square. So this is the value of moment at x is equal to L by 3. So this was L by 3 and this will be minus. So let this is minus, this point is minus 0.006172. These are very small value, you can assume. So this will be your first point. Now you can see that shear force is a second degree and the slope is decreasing. So bending moment will be again the third degree and it will be in clockwise direction. Okay. So this is your minus 0.006178 W naught L square. Again, you can see that at a distance of at 0.707 L, you have shear force is 0. So here you will get the maximum bending moment. So put x is equal to 0.707 L in equation number 4. So when you put it in equation number 4, this is your equation number 4. So when you will put that, so what will be the answer? Again, if I put it in equation, so m is equal to W naught L over 4 it will be W naught L over 4 into 0.707 L minus 0.33 L minus 1 over 6 W naught L cube over L into 0.3533. This is very simple. You have to put x is equal to 0.707 L in this equation and get simplified. You will get this. And after further simplification, you will get moment is equal to 0.006 0.036 W naught L square. So this will the moment at x is equal to 0.70 L. So let this was the point. So let this moment is this point is let this is the point which is 0.036 W naught L square. So again you can see the slope is decreasing and it will be a bending moment will be like this. Now at x is equal to L, put it in equation number 4. So when you put it in equation number 4, so you will get moment is equal to 0. You can put it by yourself in this equation and you will get the value will be equal to 0. So we will having moment at this end will be 0. Okay. So how we will again this will be a in curve form. Not a straight line. It will be in curve form. Okay. So this was all about problem 6-27. I hope you have enjoyed these videos. I have tried my best to reduce the time and to explain it very well. But you know that this problems takes too much time in solving because you have to find too many things. So again, if you want to learn it properly, you have to watch the whole video from the start. And I believe that after watching this full video, you will be able to solve such type of problems. Those who are new to my channel, then subscribe it and press the bell icon so that you can get the notification about latest video. And if you have any question, you can ask me in comment section. Thank you for watching.